Today we have Zhongqing and Tomoki-san, and also we will have Terry's practice for ASRC's talk. So I think maybe Zhongqing or Tomoki-san can go first. Want to go first?
Yeah, I can go.
Thank you, Zhongqing.
Let me share my screen. Can you see my screen?
Yes.
So today I find this paper, RFRB emitted from rotating magnetospheres searching for periodically in polarized burst. So there are research about the repeating FRB. Then because it's repeating, so uh, so they are thinking about repeating FRB is the rotating magnetosphere of the compact object. Then in the previous, the researchers want to see because it's repeating, so they want to see something undialing period, but actually they cannot find the undialing period. So the cycle is not stable. Then so they guess repeating FRB is the large duty cycle. It means that the magnetic and the rotation axis is nearby. So it seems like the period is unstable. Then, if that is true, then you can see the polarization angle of the burst should be tied to the rotational phase. So, this team proposed a new test to identify a possible stable rotation period under the assumption above. Then so the duty cycle is defined as the fraction of the rotational period in repeater for which the line of sight sample the active part is the active part of the magnetosphere. And that defined the function because they are assuming uh, the polarization position angle have the relation between the rotational phase. So let's create this function. And let me go to the result. So in figure 1, they are testing two methods. One is using original, the time of arrival, TOA. And the above panel is using the polarization angle. So in their result, the arriving time didn't show up in the high dusty cycle. But if you look at the polarization angle, the high duty cycle is appeared. So that's why in a previous work, they didn't see FRB have the uh 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 inline period. So in their research, they are using different methods using the polarization angle. And because polarization phase have two phase, I guess. One is Q and the other is U. So they also testing these two phase to see which is affect the result more. So they separate the phase to the Q and U and testing. So the result is U will affect the most. So the this period is come from U, not come from the Q. Yeah, it's very short paper. That's all. Yes.
Thank you, Zhongqing. Is there any questions?
George, I have a question.
Yes.
So this paper is showing only simulation,
Yeah.
but I thought they should be able to apply this method to observe the data, no? Because this polarization angle change is already observed, no?
Yeah, I don't know.
They need
I think they're testing not FRB. They're testing maybe radio pulse.
ah, eh, okay.
I don't know why they didn't testing FRB. Yes.
Let me try to understand. So to test this method, you need a polarization angle change for individual FRB, right? Then
Yeah.
you need this polarization angle change for each burst
Yes.
of repeating herbies. So you need
Yes, I
actually
think.
many measurements for
Yes.
polarization angle change.
I think so. Yes.
Okay, then I remember for some case, yes, they report this polarization angle change within single burst. But then I don't know if they have many of them.
Oh, yeah.
I
Maybe
don't.
less.
There may be, but they may not. Thank you. This is interesting.
Hi, Zhongqing. So, how many birds do they need to apply this method?
Good question.
Yeah.
I think they didn't discuss.
But they simulated, right? There must be number here.
Number. Sorry, I didn't measure. Number.
Okay, page 2, they say like randomly 1 to 100 rotations. Maybe this
Page
number
2.
they need. Yeah. The fifth line of right hand side.
Oh. 100 rotation.
I see.
It's 100. I mean, it's 100 a lot for repeating FR beats or not?
I think not, right? I
Just
think it's a lot.
if you require polarization angle change, this may be a lot, I think.
Oh, okay. Thank you.
Just detection number is we have more FRBs, right? Even for single repeaters. But if you require this polarization angle change for individual FRB detection, then maybe 100 is a lot, I think. I'm not sure every time they really detect this polarization angle, actually.
Okay. Thank you, Teja-san. Is there any further questions?
Johnson, I have one question.
Yes.
And I cannot understand what kind of analysis is assumed in this paper. In each observation, we can measure position angle, and what kind of analysis reveal this kind of duty cycles? Very simply, my question is how to make the figure you showed.
How to make
Is this figure? If you don't have answer now, please let me know later.
Yes.
Yeah.
I'm sorry, but
Sorry.
my I don't know, I may be wrong. My understanding is for each burst, you have polarization angle change, right? So therefore, you are looking at a part of rotation, spin rotation, for one FRB. And for another FRB, you are also looking at another part of rotation. So therefore, you have many pieces of rotations. So then if you combine all together, then you can calculate how fast it is rotating. That's my understanding.
Yes, very simply that kind of analysis, but I think at each time we just observe one position angle, right? At one first, we did one position angle, and as in other observation, we observe other position angles, and we get this kind of sequence. And from that data, how can we calculate this kind of duty cycle?
でも、ポジションアングル changes, right? Even within one FRB.
Oh, really?
I think so. I remember some people reporting this. Say, even if you look at only within one FRB light curve, position angle changes within one FRB.
So
therefore, polarization angle measurement is not one for one FRB. If I remember, I think so.
They use that kind of time evolution of polarization angle. Okay. But in that case, how can we determine duty cycle? Is it easy?
I thought that's why they can decide, because if you assume position angle change within one FRB is due to rotation, so now within one FRB time scale, so you can know how much rotation happens, right? If you assume this polarization angle change comes from rotation.
Yes, but it's about 1% of total. It's about 1% of total rotation, right? So
therefore, you need many.
You mean we may observe many times and
many different parts of rotation. Then they try to combine all together.
Then we can find some kind of some smooth Arcs. Ah, okay.
I don't know. My understanding, yes.
Oh.
I don't know. I may misunderstand.
Okay, thank you very much. Then I think we can do it.
Okay,
Thank you.
for
Thank you very much.
discussion. Yeah, I think time's up. So thank you, Dongqin, and then we move on to Tomoki-san.
Okay, let me share my screen. Okay, today I'd like to introduce this paper. This paper is a theoretical paper about FRB. They consider time evolution of rotation measure and dispersion measure in this paper. It's also very short paper. Recently, the sudden change in rotation measure is observed for this FRBs. The data is like this. This right panel shows the rotation measure change and time, and it's constant for many times for some from here to here, it's constant, but it suddenly rises and gradually decreases and back to initial values. And they want to explain this kind of signature by some very simple models. And here is the assumption. They consider neutron star, magnetar flares, because in magnetar flares, some baryonic components, such as proton or so proton or helium is ejected to the magnet spheres. And if FRB propagate from here to here, then some rotation measure is created in this region. This is due to here there is protons here. So if there is no protons in this region, if rotation measure is not created during propagation. But due to the protons emitted in the magnetar flare, rotation measure rotation measure is created during propagation from here to here. And this is what they do. And they consider very details, and similar to binary neutron star measure case, they assume some velocity profile of this ejector, and they assume that the ejector is initially hot and fully ionized, and as it propagates, it experiences adiabatic cooling and its temperature decreases. And at some radius, the temperature is enough low that proton and electron recombinate. And they take this effect into account. And maybe they also consider synchrotron cooling and peripheral absorptions. And assuming this kind of profile and physical process, they estimate the rotation measure and dispersion measure included that arise during propagation during the propagation of this baryonic ejector. And they plot many parameter surveys, but I will skip very details. And this is their result. And they did some MCMC Monte Carlo MCMC survey, and they find very good parameters for these FRBs. And maybe here is the result of maybe here is their result. And the top panel shows the rotation measure change from this model. And bottom panel shows the dispersion measure change in this model. This model, the dispersion measure, it's a change in dispersion measure. It's very small and it's within the observational fluctuations. And they can explain sudden rise and decrease of rotation measure by this time. And they also did consider the galactic FRBs and find that under some assumptions, this kind of trend is not observable in magnet arcades. And that's all. So in summary, they consider this kind of mass baryon ejection in magnetar flare and calculates the time evolution of dispersion measure and rotation measure. And they get good agreement with observations. Okay, that's all.
Thank you, Tomoki-san. So, Shotaro, please go. Shotaro-san, do you want to say something?
Yeah, I'm checking my microphone. Do you hear me well now?
Yes.
Okay, so my question is about what is the total energy of this mass ejection? What's the kinetic energy of this flare ejector?
Tomoki-san, you're muted.
Okay, it's they assume the energy is below the magnetar giant flares. In this case,
I think everything is always below magnetar flare, giant flare. So my question is how rare this kind of flare can happen?
You mean event rate?
No, I mean, yeah, whichever is fine. So basically, how rare this kind of ejection?
How rare?
Yeah, so okay, let me explain. So because if this kind of mass ejection happens every time when FRB is created, we should see this kind of rotation measure change very often. So this kind of event must be very rare. This means the energy of this magnetar flare ejection must be very high. Otherwise, we should see more this kind of rotation measure change.
Okay, I understand. Thank you very much. Sorry, I missed the total energy, but どこだっけ in case of galactic FRB, they assume total X-ray burst energy is about 10 to 39 ergs.
No, I'm asking about this event.
At this event, I say just it may depend on the baryon loading parameters because X-ray is emitted from fireball and almost all energy is by photon and electron position plasmas, and maybe this how baryon is contaminated in this ejector is difficult to calculate.
What's the typical baryon load parameter compared to, for example, baryon load parameter eta, for example? What kind of value they assume? Do they assume extreme value?
No. They don't assume baryon loading parameters. They just calculate how much baryon is emitted from this system.
Okay, then how this baryon ejection compared to our galactic giant magnetar flare happened before?
So maybe then we can calculate. Ejector mass is then this value, and rest mass energy of a baryon is about 42 eV, maybe 42 or so. And if baryon loading parameter is 100 or 1,000, then we can calculate 42 45 total X-ray energy is about 10 to 45 or so, I think.
So it's around giant flare, magnetar giant flare.
Yes, yes.
So okay, then maybe the question. So basically, what makes difference in the rotation measure is the amount of barium rather than the, of course, the energy of the maybe emission. It's X-ray emission must be also high, but this kind of event we shouldn't see that often.
Yes, yes.
Okay, thank you.
From this Monte Carlo calculation.
Then I also have a question. So when before this rotation measure change, there is a period when we don't see any FRBD on this whether panel B or panel A before the 50 days. So do they have monitoring during this time, or they didn't just observe?
Sorry, I don't know.
Okay. I wonder, it depends. Maybe if this kind of mass ejection happens, we should see suppression of radio emission. So I wonder, they also consider this kind of effect?
Yes, they can consider a peripheral absorption for radio burst. And there made some comments, but I missed.
Okay, thank you.
Yes, of course, they consider absorption. Thank you very much.
Sorry, can I ask one quick question?
Yes.
In figure 6, so could you go to figure 6? I was wondering, say, if this model prediction is the case, so we expect a sudden change in DM too, right?
Yes.
Then fortunately, there is no data in this raging part. So then, but in rotation measure, they saw this sudden change, but not in DM. This means, say, it seems that there is a time lag between DM sudden change and rotation measure sudden change. This is the reason why their prediction of sudden change in DM is outside observation. So we don't see data points, right?
Yes, you mean here?
So, yeah. We don't see data points here, fortunately. So that's why this is not conflict with data points. But then I wonder what makes this time lag? Say, sudden jump really happens in DM, maybe t equals 0, right?
Yes.
And then rotation measure, there's offset, no?
Oh, yes, that's right.
Because rotation measure and DM, they should be measured at the same time, right? Because they are both measured from FRB.
Yes.
So therefore, data points should be the same time, I think, for DM and the RM. Then one aligned with rotation measure, but another is offset, right? This is the reason why there's no conflict in DM. So why this happens?
Maybe the total change of the dispersion measure in this scenario is very small.
But then model prediction is large, no?
No, it's very small.
Huh? Sorry, I thought the solid line is model prediction.
Yes, this solid line is this blue line.
Blue line.
Yes, model prediction.
But then, fortunately, we don't have observation during the sudden change in DM.
Yes, there was no FRP observation here. Yes.
So maybe the key point is B field rather than the number density of electron.
Yes.
So B field must be very high, efficiently become very high. So only rotation measure is enhanced to extreme value, while DM only traces number density. Therefore, it doesn't have much change. Yes, but how do they have equation? Scaling relation.
Or more like I want to know time lag.
There is no time lag.
Ashimoto-san, I think time lag is due to the y-axis range of this figure. If we zoom very small DM region around here, then this blue curve maybe become something like this.
Oh, okay. I see.
So the point is absolute value of DM and rotation measure enhancements are huge, very different. So
Yes.
this is because the rotation measure traces magnetic field. Maybe they consider the region which is very close to neutron star. Therefore, still B field is background B field is very high. I don't know.
Yes. That's right. That's why. Sorry, no scaling relation, but something like this. This is DM is determined by this relation, and setting the DM very small value, but B is very large because this is very near the magnetars, and that's why rotation measure can be very large, can become very large in their calculation.
I see.
Okay, thank you, Tomoki-san.
Thank you very
Hands
much.
up. Yes. So thank you, and we move on to Terry. So the talk is 12 minutes plus 3 minutes QA, right? I think.
Yeah, 12 minutes. So, hello everyone. My name is Terry from National Tsinghua University, and my talk today is about what if planet 9 is currently is perihelion. So, in this talk, I first show you the motivation why we choose this project, and I introduce the data set I use in this work, and also the selection process. Then I will show you the result and the future work. So let's get started. So let's back to more than 10 years ago when analyzing the orbit of minor body object, minor object in the Kuiper belt. People found that these objects show peculiar orbital clustering, not only in the argument of perihelion, but also in the physical space. And one of the famous simulation work, which is Patigan and Brown in 2026, they suggest that the probability for this orbital clustering happen due to chance is only 0.007%, which is almost impossible. And they also suggest that a giant distant planet with at least 10 Earth mass and the semi-major axis about 700 AU can maintain this orbital clustering. And from the semi-major axis and the eccentricity, we can estimate the perihelion and the aphelion of Planet 9, which is 280 AU and 1,120 AU. And from the illustration image of Planet 9, we can see even at the perihelion, Planet 9 is still very far away from Neptune. And so how to find it? The most important question is, are there any challenges in finding Planet 9? The answer is yes, because Planet 9 is very far away from Earth, so the reflected sunlight degenerates very fast as a function of distance power -4, while the thermal radiation from Planet 9 only decreased by the function of d power -2. So from this point, we know that the infrared survey is way better than the optical surveys. But on the other hand, the infrared light would be absorbed by the Earth's atmosphere. So it's better to use the space telescope rather than the ground-based telescope. And from these two arguments, we choose the infrared survey with space telescope to conduct our research.
Actually, in the past, there are many search for Planet 9 using optical survey, but they fail without constraining any Planet 9 candidate. And one of the reasons is because we don't know where Planet 9 is on its orbit. So that's why we need the all-sky surveys to search for Planet 9. And there are two all-sky surveys that meet the requirement, which is the infrared astronomical satellite and the Archery Space Telescope. And the co-author of this work is the part of the Archery project. So this is one of our advantage. And the IRAS and the Archery have 4 different filters in far infrared wavelength. And we use 4 different data sets for the IRAS and 1 data set for Archery. But we don't use the public data of Archery because of the requirement for multiple detection at the same position after 6 months. So they automatically remove the moving source. So here we use another dedicated source list for Archery for the Planet 9 search, which is the monthly unconfirmed source list, include moving source without monthly confirmation. And in total, we have more than 2 million sources for IRAS and Archery, and the detection limit here it depends on the wavelength and the catalog itself. So our Archery source list include the possible source fainter than source in the public catalog, for example, the bright source catalog version 1 and version 2. And the epoch difference between IRAS and Archery is 23 years, which is large enough to detect the slow motion of Planet 9. And our previous work searched for Planet 9 with the distance range from 500 to 700 AU. And we found one good candidate, and this work was accepted for publication in PASA. And it's our honor to have our paper featured on Science magazine and other news media, which is a good chance to have our paper approach more audience. And the idea to select Planet 9 candidate is we apply a set of positional and flood criteria. But the general idea is we search for moving object. But before that, we need to make sure all of the object above the detection limit of IRAS and Archery, and then we make a possible candidate pair, which include 1 IRAS source and 1 Archery source. So we expect that at the beginning, IRAS, the Planet 9, we will detect it in IRAS, and then after 23 years, it will move to another Archery position with the angular separation between 70 arcminutes to 166 arcminutes. This corresponding to the distance range of 280 to 500 AU. And before the visual image inspection, we have 643 IRAS and Archery pairs. And 640 pairs were included because one of the image was contaminated by the galactic cirrus region, and only 3 good pairs in the final list. And here I will show you one of the examples of our good candidate. The left panel is the Archery image, and the right panel is the left panel is the IRAS image, and the right panel is the Archery image. So we expect that the Planet 9 will move from the green circle on the left panel to another position at the white circle on the right panel. And here the angular separation is 165.7, which is very close to the upper limit of angular separation range. And it suggests that if this candidate is planet 9, then it could be currently very close to its predicted perihelion. And we do another test by checking the Akari probability detection map to see if our object is fast moving or slow moving object. And here's the result. We have 2 detections in the second row on the same date, and there's no detection on other panel of 6 months on the day of 6 months before and 1 year before. And this suggests that our object is most likely a slow moving object. And because IRAS and Akari detection itself cannot constrain the full orbit of our candidate, so that's why we need follow-up observation by using the Subaru hyperspectrogram or dark energy camera to have more detection, and it will help to constrain the full orbit of our candidate. And these 2 surveys with only 1 hour of exposure time can detect the distant moving object as faint as 26 magnitude. And we also estimate the angular separation range for the epoch of 19 years from Akari to 2025. And in summary, we already take advantage of far infrared surveys to search for planet 9, and out of 643, only 3 good candidates with slow moving Akari source, and one of them is most likely near the perihelion, the predicted perihelion, and we need follow-up observation to determine the full orbit of our candidate. So thank you very much.
Thank you, sir. So it takes 10 minutes, 34 seconds. So good time. And yeah, I think you can add something. Yeah, you have time to add something. So
Yes.
first, you go to the fast and slow moving object. I think
This one.
next page. So I believe we have a lot of examples. So I think you can show one fast moving object here. I think one slide is like, so you can clearly compare what is fast and what is slow. Maybe not this one. Maybe like I don't know. Maybe I can give you one like the famous.
Like this one, right? Because we only have 2 detections.
Oh, no. Let's I mean, I thought you are saying fast moving object like this one, like 1 hour is like they move 1 arc minute per or 10 arc minutes per hour, something like that. I thought you are talking about that. I have many examples I can give you maybe.
Oh.
Yes. I thought you were saying something like this. They move very fast. So maybe they are nearby at asteroids, not planet 9.
Yeah. And it's also one example that they don't have. It doesn't have much hourly confirmation. No hourly confirmation because we only have 2 detection, right? And other 2 is non-detection. Yeah. On the same date.
And also, I think you mentioned in the middle that your previous work is accepted for publication in PASA. I think you can move this to the second page. You should emphasize this first. I think, like, emphasize your work is accepted and also the news. I think you should put that in the first 2 pages. Then the audience will be more concentrated and interested in your work, I think.
Yeah, because I need to give an overview first and show why the infrared survey is better than optical survey. Then we show our work, our previous work use infrared survey is accepted.
So when you give an overview, I think why don't you show simple SCD, which picks in the far infrared? You didn't show anything like that, right? It's kind of simple SCD, which picks in the far infrared. So that's why you need a far infrared data, right? Simply, just simply. So you didn't show any figure, so you just show the text and table. So which one? The contents is okay. I'm something like this. I think you need to show this first. In the first or two.
Yeah, so currently
Number one or two
I put
slide.
it in the backup slide, so I can move it to the first slide.
Yeah. But yeah, you just don't need it. This kind of figure, just simple curve which picks. This is far IR. That's enough, right? This is already too difficult to understand. You know, spectral radiance. We don't use this kind of things, right? I'm talking about just this kind of curve and then arrow, far infrared, something like that. And then when you say orbital clustering, I think it would be better to show without dotted ellipse. When you say orbital clustering first, I think it would be. Can you go back to the slide first or second slide? Yeah. So when you show this figure, you are talking about orbital clustering, right? When you say this word first, I think you better without this dotted circle. And then when you say expected plane, then okay, this dotted circle, ellipse appears. I think that would be better.
And also, I think the logic flow should change. So you should show the animation first. Like you should show the animation of moving source. Then you introduce Akari and Iris. I mean, you suddenly introduce Iris and Akari, then nobody knows why you are using two different surveys. I think you should put this as first.
So you just spent 10 minutes, right? You still have 2 minutes, right? I think you just can add this kind of things. So I think you didn't mention the importance of or meaning of this work, impact to the astronomy or history of the solar system, something like that. I think this has to come first.
Yeah. If we change the history of
the
solar system, yeah.
Even human society. Because somebody was really sad because Pluto was kicked out of the solar system. So I think you can make them happier. No, we have a 29 here, something like that.
So, but many of them always say that why not Pluto?
Yeah.
Why not Pluto?
But Pluto is really small, but this is huge.
Yes.
Maybe you can show this kind of orbital cluster. I think you have to say that kind of thing first. And then why and far infrared, and then he said, this paper is appeared, so many media here and there. And then I think you said our previous paper, I think not previous paper, it's current new paper, right? When you say previous paper, it sounds really old.
Yeah,
probably it's kind of several months ago.
Recent work.
And our recent work or new work.
Okay.
Previous work sounds really old paper, right?
And I think you didn't emphasize the difference between our recent work and your new work. The search radius difference, did you emphasize this or not?
Difference between new work and
previously.
Yeah. Because we want to narrow down the distance range.
Yeah. You should say this.
Yeah.
You can say
I-
follow-up research.
I forgot to
You can-
mention
Our
that.
recent paper and follow.
Yeah. This is a follow-up of our previous work.
Yeah, I forgot to mention that.
Oh, can I also say something?
Yes.
Sorry. I really want to come back to Yuan's point. I agree with Yuan's point, saying that this press release, say, featured by many media, I think you can emphasize this at the very beginning. Say, for example, you can did you present to the previous talk in ASRC? I mean, Planet 9.
Yeah, I think
I present Planet 9 in ISLC last year, but
Last year, right?
the result changed a lot.
But that's fine. But then that finally published, right?
Yeah.
Therefore, I think you can say something. I presented this result in last SRC meeting, and then finally this becomes a science magazine or something like that. Then you present continuous work from that. Then I personally prefer this order then, because as you mentioned, if you say, oh, this was featured by science, then you get attention, right? So therefore, you can say this at the very beginning. Then that's maybe most important part. And then I have some minor comments.
Yes.
So could you go to the Akari image? Akari and Iris image. You have triangle. This one. Could you draw, say, arrow? Say this is people just want to know this moved from which to which. Then I can see arrow both sides. Therefore, could you put the arrow, say, from which to which?
Actually, this is the arrow, but
it's
too small.
Yeah, too small. Yeah, so
And then I can also see arrow both sides, no? You are putting arrows both sides, no? So it should be one way, right?
Yes, this is how we measure the angular.
No. This is saying that
put the arrow
from here to there.
Oh,
so you want
this
to add
current
one way.
line supposed to be moved, right? So this move from top to
add the
bottom,
arrow
bottom
to
top.
show the direction, right?
On direction.
And I personally think that, the size of the circle is too small. So that people then doesn't know, inside this circle, if there's something inside the circle or not. So I think you need an additional arrow, flickering arrow.
Did you understand my comment? Sorry, Terry. I want to put the arrow from which to which to understand it moves from which to which.
Yes.
Then people understand which figure I have to see, right? Say, if it moved from Iris to Akari, then, okay, so we should see the detection in Iris image. And then we should see the detection in Akari image, something like that, right? So I need an arrow here to understand this. And also, could you go to animation? I think that was very good. And then I think it's good to put the year of observation. Say you are saying after 23 years, but you can also put the year of Iris. Say, and also year of Akari. That's maybe easy to understand. I think that's all from me.
Yeah. Thank you very much.
Below the name of the telescope. Below the telescope, you need to put ear, right?
Yeah.
And also, I think you forgot to explain why we don't see anything in Akari's image.
A co-edit. Right?
Yeah, because it is co-edit image. It appears only, 2 out of 11 co-edit image.
Mm.
So we don't expect we can see it on public image. Then you go to per scan image. Right.
You need to make this clear. This is not public available image, right?
Mm. This coordinate is different from the
This is different from
the public data.
you did reanalysis, right?
Mm. Yeah, but sometimes we see the source, but sometimes we did that, like this one.
Yeah, but I think the one you showed, we didn't see anything, so you should explain this one.
Mm. Yeah, like this one, we see the bright source here. Yeah.
I think this is also confusing. Akari source appears in IRS image.
Yes, this is the bad candidate. So I put it in the backup
This is
slide.
backup, right?
Yeah.
This sounds like Akari source is, Akari telescope is previous than IRAS. IRAS source disappeared in Akari image, right?
Yeah,
Because
but
it's 23 years later.
but we expect that Akari source should be absent in the
I
IRAS
think we
image.
are going into two detailed things we can discuss later. Then I think we should close Astro-ph first. Then first we should decide who want to present tomorrow. So I will practice tomorrow, and we need 2 more volunteers. Who wants to volunteer tomorrow? Astro-ph. Anyone? Maybe.
I can do that.
Oh, thank you, Teja-san. Then, okay, I will ask Kosas. So, hopefully tomorrow we will have Teja-san, Kosas, and me. Okay, thank you everyone. Then see you tomorrow.
See you tomorrow.
You-
Bye.
Bye.
Bye bye.
My